Well, hello again. In this example, you will learn how to generate numerically based influence lines for beams. Specifically, we will be taking a look at this multi-span beam, and we're being asked to identify the influence lines for three separate responses. That for RAY, the reaction of A, the shear at section 1-1, that's this one right here, and also the moment at that location. We are being asked to provide values at 6-foot intervals along the length of the beam. First order of business is going to be to identify the determinacy, and so if we look at this, we can identify these as being our external reactions. That means the total number of unknown forces that we have, 4. We haven't made any cuts, so the number of structural pieces we have is 1. So the total number of equations of equilibrium that we've got will be 3. 4 minus 3 then produces the information that we are statically indeterminate to the first degree. So what we will do is we will go ahead and select RAY as the redundant. I could have just as easily selected RBY or RCY as my redundant, but for this example we selected RAY. Now the process of this is that we will remove the support at point A and we will replace it with a unit force. Now that I've got that done, I'm going to go ahead and sketch what the deflected shape looks like as it is subjected to that particular force. So we have placed the force at the point A. I've given a rough sketch of the deflected shape. For ease in communication, I've gone ahead and labeled each of our intervals, numbering them 1 through 11. Now the task at hand is going to be that I need to identify what the deflection is due to that unit load at each of these individual stations. So you're going to have to stop and think about how one would do that given the tools and techniques that you already know. Two things come to mind here. One would be virtual work. The other would be the use of beam charts and the principle of superposition. So I will use beam charts to compute these deflections. I'm going to use the principle of superposition. So what we notice is that from B to C it is a simple supported beam. And so I'm going to consider from the far left to point B to be a cantilever, and I'll go ahead and apply a unit load here. Let me go ahead and sketch the deflected shape in here. Recognize, and I'm going to demonstrate this simply for one of the deflections. We will look here at this value of delta 2. This develops a moment here of 24 feet. The reason it's not kip feet is because I just gave a unit load that didn't have units. We of course have this reaction here that is 1. Okay, what I will do is I can look at a beam chart, one that has a point load on it, cantilever beam, and if I recognize that in my particular case I need to be looking at what the distance is to that point load and also what the coordinate is for my desired deflection, which in this case also happens to be at the same location. So I will use values in here of A equals 24 feet and X equals 24 feet, and I will go ahead and use this equation right here. So plugging in those values, I can get this quantity for delta 2 to be equal to 4608 divided by EI. Then I need to come back here and I need to handle the other half of this, and that is I will take that moment reaction and I will go ahead and apply it in an equal and opposite direction at point B, and I then need to go ahead and sketch the deflected shape for that, remembering that what I'm looking for here is I'm looking for that quantity as well. So you'll recall that we had this. It was being 4608 divided by EI, and I will then get this one down here from that superposition as well. So in looking at this beam chart, I can get the rotation at location 1 by using this, and I will plug in a moment of 24 and also a length of 24. Now that doesn't give me the deflection where I need to know it, but rather it tells me what this rotation is here as we come through. And so this is 192 over EI. What I'm needing is I'm needing that displacement at 2, so I'll just do that using small angle theory. delta 2 is equal to 192 over EI multiplied by the length. So that's the distance from the pivot point B over to delta 2. And that will then be equal to 4608 over EI. That means that my total displacement at delta 2 due to that unit load at A is equal to 4608 over EI plus 4608 over EI, thus giving me 9216 over EI. So I'm going to go back here and I'm going to label that as being the displacement. So 9216 over EI. That's for point 2. In fact, let me go ahead and give us a little arrow there. And then what we will do is we will follow the same approach, and I realize it can be a bit of work, but using beam charts we can go ahead and find the displacements at each of the other locations. So these would be the values of the displacements to occur. So with those displacements in hand, we now need to move on to the task of normalizing these. We normalize by taking all of these deflection quantities that we now have, and we divide them by the quantity of delta 2. Why delta 2? Because that's where we had placed the unit load. So let me give an example here. Delta 1, I would take that quantity, 12096, I'll divide by EI, and I will divide that by 9216 by EI, and that will come up to be 1.313. In a like fashion, delta 2 would have 9216 divided by 9216. That will be equal to 1.0. Delta 3 would be 6372 divided by 9216. That will be 0.691. And I would do that for all the individual locations. Now you can rest assured that you have done things correctly, or that you're normalizing by the correct value, if the displacement that you get at the location of your redundant, so that's the location of the point load that you've applied, should work out to be 1.0. And none of my deflection terms should have any EI values in them. Those should have all canceled out as we went through the process. Okay, so the next task is going to be to take those values that we get, those deflection values, and generate the influence line for the reaction at AY. The influence line is nothing more than those deflection quantities that we got. So for instance, we had here a value of 1.0, we had here a value of 1.313, 0.691, and then we can proceed through and label the values for all the other situations. And this is what that influence looks like as we plot those displacements that we had computed. Please be aware that it is always essential for you to develop the influence line for that redundant force first, because that is going to be the tool that lets us develop the other influence lines that we are going to be dealing with. So with this influence line in hand, we can then go on to developing the influence lines for the other two quantities of interest for us, the V11 and the M11. Now in order to find those, what we will do is go ahead and make a cut through our structure at that section 11. And let me just go ahead and label these as being the unknown quantities. And we will then take the approach of taking a unit load and just moving it across the structure at the different locations. So in other words, at the 6-foot intervals that we were dealing with. So if I place it to the far left, I've made a cut at section 11. I will then need to go ahead and get this reaction here. Now the way we get that reaction is we can go back and look at the influence line and say, hey, when that point load is to the far left, the reaction at AY is going to be 1.313. So I'll go ahead and put that in there, 1.313. And then I simply have to use equilibrium to solve for my unknown quantities because we've got them there. So if I sum forces in the y, I will find out that the shear is equal to 0.313, and if I sum moments about the cut, I will then be able to find out that the internal moment is equal to negative 2.24. So since the point load is to the far left, what I can do is I can begin to plot these on my influence lines, V1-1, M1-1, and the units on this going to be feet. So I'll go ahead and plot this out. This is 0.313, and this down here is negative 2.24. Now what I'm going to do is I'm going to go ahead and place the point load at the next increment over. That is this one. Remembering that I'm still looking for the internal moment and internal shear at that particular location, and I will need this reaction right there. Once again, I will go back to the influence line to see what that reaction is, put it on my free body diagram, and then I can run my equilibrium equations. Then go ahead and plot that on that influence line. So let me show you this explicitly for one more scenario. I'll place the unit load here at 6 feet out. I go back to my influence line for RAY and I see what the reaction is, 0.691. I do have that internal shear and internal moment. I will then run the equilibrium equations on that, find out that shear is equal to negative 0.309 and moment is equal to 2.29. Then I need to go ahead and plot those on my diagrams here. The negative 0.309, and this one is 2.29. Now moving on to the next location, I'm going to place that unit load just to the left of the cut at point 1. I can solve for the internal moment to be 4.87 given that reaction of 0.406. I can then solve for that internal shear to be negative 0.594. But as you may recall, we also look at the scenario where that unit load is placed just to the right of the cut instead. That doesn't affect what the internal moment is that we calculate, but it would affect what the internal shear is that we calculate at that location. And that would turn out to be 0.406. We can go ahead and plot those on our influence lines here. So here we've got that 0.594, and then just to the right of that it jumps up to 0.406, and that moment is coming up here 4.87. Okay, we will do that process for the remaining points, and then we'll be able to sketch our influence lines. And this is what the completed influence lines would look like for the internal shear at 1 and the internal moment at 1. That concludes this example. As always, it's a beautiful day for studying structures.